Mais um vídeo aqui para o YouTube. Ahá! Hoje vamos ver Science Time. Brian Cox explica o paradoxo de Fermi. Não faço ideia o que é que seja o paradoxo de Fermi. Não faço ideia quem é que seja este maluco. Sugeriram no chat. Vamos ver. Estavam a dizer que é sobre vida alienígena, PhD em física. Ei, inglês! Não tem legendas em português. Há aqueles que não. Então levam com o inglês e traduzam.
Gazed at the stars and wondered, are we truly alone?
Ei, é bem, isto vou-me tripar todo, já estou mesmo a sentir.
Billions of suns
Mas está
blaze
com boa
across our
edição.
galaxy, each offering the possibility of alien worlds teeming with life.
A câmera do lado direito não está para as legendas. Eu disse que depende de uma beca, acho eu. Se as legendas forem grandes vai tapar.
Yet,
Mas nem reparei que estava à frente. No meu ecrã não estou à frente. Esta merda também dá para ouvir, foda-se. E aposto que as legendas até estão mal, algumas.
look up at the night sky for signals, we are met with silence. This begs the question.
Epá, mas as legendas estão bué da apagadas. Isto não dá para as pôr mais visíveis.
If extremely
Mas
rare
parece
or just
não
hard
tão
to
cá.
detect.
I'm always interested
É mais
in
bisga de som.
questions where there's a
Isto está bué
collision
da
of
alto já.
ideas that appear
Isto está quase ao mesmo nível que o meu
irreconcilable,
micro.
right? They don't fit with
Aqui
each
no
other.
misturador.
And I think that that collision of ideas in cosmology is very vivid when you bring it together with biology, which is that we are physically insignificant, but it is possible to argue that we are remarkably valuable, notwithstanding our physical insignificance, because it's possible to at least argue that the number of civilizations in a galaxy like the Milky Way might be, on average, 1 or less.
Our galaxy, the Milky Way, is estimated to contain between 100 and 400 billion stars, and at least as many planets. A new study suggests there could be 60 billion planets in our galaxy.
Pá, por acaso cenas com o espaço, tipo, e estas dimensões absurdas, eu tripo-me todo. Tipo, é mesmo uma cena abismal. Tipo, são mesmo dimensões, pá, inimagináveis. Tipo, eu não consigo tipo, conceber na minha cabeça a ideia que é uma cena assim tão grande. Não consigo tipo, pensar numa cena assim tão grande. É mesmo impossível.
Habitable zones, regions capable of supporting life. For a planet to support life as we know it must have liquid water.
Pá, e depois é bué estranho como é que numa cena tão grande, mas pronto, é estas teorias e o caralho. Como é que só se sabe que só o nosso planeta é que teve vida, só o nosso planeta é que reuniu aquelas condições todas buedas específicas, tipo os pormenorzinhos todos buedas específicos para ter desenvolvido vida. É bué estranho, numa cena tão grande, uma imensidão tipo gigantérrima. Como é que tipo, não sei. Mas se calhar é tão grande, se calhar para lá, para outro sítio qualquer na outra ponta, se calhar há vida, não dá é para saber porque não se chega lá. Não sabem, mas também não provas ainda porque não viram nada. Pois.
Water, energy and nutrients. These basic ingredients appear to be common throughout the universe, but we have yet to find evidence of other civilizations. So, where is everybody?
Pois é
Well, it's
isso.
the Fermi paradox. So the Fermi paradox, going back to the great physicist Enrico Fermi, is essentially the question, where are they? You base that on the observation that, let's say there are somewhere between 200 and 400 billion suns in the Milky Way, something like that. We think a lot of them have planets. Many of them have potentially Earth-like planets. So you have 13 billion years of time. You have hundreds of billions of suns. probably trillions of planets. And so
Caralho,
it is a
trilhões de
reasonable question
planetas.
to ask, why not? Why has a civilization not arisen ahead of us? So let's say 1 billion years before us. Why has no civilization escaped its home world, apparently, and essentially written its existence across the sky? Why is that? Why don't we see anybody? One of the arguments is often framed in terms of self-replicating machines, so-called von Neumann machines, after the great mathematician John von Neumann. And so essentially the idea is that what are we? What's a human being? It's a replicator, right? So it's a physical object. It operates according to laws of physics. That's what we do, and we replicate. And so it seems that there's no reason why we couldn't build replicators that are essentially, you know, AIs, basically, right? It's almost like an AI-controlled 3D printer with some mining stuff attached to it, and you send it off to the asteroids or to Mars or to the next, to Alpha Centauri, to the system there with, and all the raw materials will be there to allow this thing to replicate. And then you can build a kind of a model of that, how those replicators might spread throughout a galaxy. And people have done this, of course. There's a great book, as an aside, I would recommend, by John Barrow and Frank Tipler, which is a huge influence on me, called The Anthropic Cosmological Principle. And it's a very famous book. There's a great series of calculations in there just showing you how you might estimate if you could build one of these self-replicating machines. How long would it take, given some reasonable technology, to move between star systems? How long might it take to replicate itself? And you end up with calculations that say that if someone had done that, even a few 100 million years ago, those machines would be everywhere. It's like a virus, right? In a sense, it just propagates. It's an exponential growth of these things. And so you would cover the galaxy in them. And it is true that we haven't observed any. So you might say that that's evidence that nobody ever did it. Or, in the spirit of being scientific about it, you could think, well, yeah, maybe these replicators are the size of a phone. You know, maybe they're tiny. Maybe they're so advanced that they're in the solar system and we don't recognize them. So you can argue about the Fermi paradox.
A questão é que também podes argumentar o que te apetecer, na verdade. Bom dia, Quinas. Tipo, podes literalmente argumentar o que te apetecer porque não há nada propriamente provado, nem nada. Não há nada. É tudo meio
Broadly
especulações.
speaking, it's the observation.
É tudo probabilidades e merdas.
We've looked a bit, and all our observations in the history of astronomy, of all the observations we've made, we have never seen evidence of anyone else. And so that's the and it is a paradox because there's been so much time and so many planets, and it would seem as if somebody should have done something.
Exato.
And they haven't, as far as we can tell.
Research
Mais ou menos. Já vi também uma teoria que uma vez se foi enviado um sinal e captado aqui na Terra e depois nunca mais se viu esse sinal. Fica um sinal, já não me lembro.
in the Fermi
Mas era um
paradox
sinal qualquer
often considers that
específico.
advanced civilizations might not last long enough to be easily detectable. They may be transient on a cosmic scale, meaning they
capaz de ser
arise
isso.
and then disappear, due to factors like self-destruction or natural catastrophe.
Puta, eu antes também colava bué nestas teorias, já não me lembro de metade.
Researchers argue that
Isto é
if
uma cena que me
technological
fascina bué, mas ao
civilizations
mesmo tempo fico todo
routinely
tripado.
self-destroy or otherwise burn out, then the chances of overlapping with our own window of detectability become very small. This short lifetime would explain why we don't see evidence of them today.
Carl Sagan famously said it's possible that civilizations don't get beyond this stage that we're at. So when you industrialize as a civilization, so the pre-spaceflight era or pre-interstellar flight era, you will hit problems which are probably common to all civilizations because they're just part of the laws of physics. So one of them is the challenge you pose to the climate of your planet. As you industrialize and build a bigger civilization, you'll use resources, you will affect the atmosphere of the planet and so on. So there's a challenge and you have to manage that. There's the development of nuclear weapons, for example. So at some point, you will develop nuclear physics if you're going to be a spacefaring civilization. So you will develop the ability to destroy yourself, which is kind of, you know, it's not long.
Yeah.
We go back 100 years and we didn't have the capability to destroy ourselves. Now we could. We could choose to destroy our civilization. So it may be that those challenges are very difficult to navigate. It may be just kind of one of those, not quite a law of nature, but
E se calhar é essa cena que vais evoluindo, vais tendo mais capacidades e acabas-te a destruir, e então acho que é isso que ele está a dizer. E então nunca nenhuma civilização chegou ao ponto de conseguir expandir, porque o fim é sempre que acabas por destruir o teu planeta e a tua civilização.
a law of societies
Com
that
tanto
they're
avanço de
just not
tecnologia.
able to navigate the challenges that industrialization and the development in nuclear science and so on raise. We haven't passed that test yet. So, you know, there's a name for it. It's called the Great Filter. So one of the arguments, so what we're asking here is there a filter that, let's say the filter.
E assumindo que isto aconteceu, tipo, que houve outras civilizações que se destruíram, será que também tiveram este pensamento do tipo, como é que nunca vimos ninguém? E também tiveram este processo todo de, ok, se calhar porque se destruíram antes de conseguirem ver alguém, então nós vamos tentar que isso não aconteça e vamos ser nós os primeiros.
So let's say that it's just the difficult.
É que isto depois já começa a entrar numa cena também,
to go from single cell life to
sei lá,
multicellular life. And that does look difficult, by the way.
meio de universos paralelos e que as coisas se repetem simplesmente.
Maybe it just doesn't happen very much. So there are microbes everywhere and nothing very complex. Then we'd be happy, right? Because we've gone through the filter. But it could be the filter is in our future. It could be that it's now that you get this capability to affect your planet or destroy yourselves through war or whatever it is. That's a filter, and we're approaching it. And it could be we don't pass through it. And that would also be a solution to the Fermi paradox.
Many people in the general public feel the Fermi paradox needs no solution because they believe aliens have already visited us. However, in science, extraordinary claims demand extraordinary evidence. One related idea is the zoo hypothesis, which suggests that advanced extraterrestrial civilizations do exist, but intentionally choose not to interact with us, much like zookeepers who keep animals in a zoo.
Okay. Yeah, I mean, I suppose you have to accept it's possible, except that the zookeepers don't hide themselves from the animals. You know, so you could say they're pretty good at it. We're getting better at observing
no fundo tens que respeitar todas as teorias.
Signals in the universe and so on.
Não,
so
acho que
they're
não.
doing a really good job. If they're
se calhar até era modelo do Star Wars, mas acho que não era.
Continually avoiding, so I don't know.
Também não sei as naves todas do Star Wars.
Recent estimates using the Drake equation
Caralho, mas está com uma edição gira, está com vídeos bonitos. Estes aqui.
Potentially only one. The human race. While earlier estimates were much more optimistic, this updated perspective takes into account the possibility that civilizations may not last long enough to become a spacefaring civilization.
But we don't know how many civilizations might there be in a galaxy like the Milky Way, for example. We don't know the answer. How many worlds support life in the Milky Way galaxy? We don't know the answer. We only know of one at the moment. Although I think most people would guess that surely there must be other places, even perhaps within our solar system, where life exists. But we don't know that at the moment. And so what ultimately we can say, I believe, is that we should behave as if we're the only civilization currently present in the Milky Way. That should be our approach to the way that we manage our civilization and our planet and the way that we plan our future, even though it might not be right, because we have no data, essentially.
Ultimately, the Great Filter hypothesis should serve as a wake-up call. It reminds us that if detectable civilizations are indeed rare, perhaps because many self-destruct before reaching advanced spacefaring stages, then we must be vigilant in safeguarding our own survival. In essence, if we are alone in the Milky Way, our failure to overcome our own challenges could extinguish the candle of consciousness in our galaxy forever.
I think it was Carl Sagan again who asked if a civilization like ours becomes a spacefaring civilization, so multiplanetary and then interstellar, then you have to have solved these problems that cause us to be violent, predatory. And so he suggested that as you make progress and become more powerful and navigate these problems, as we said, these filters that may lie in the future. So you have to, for example, learn to get on as a planet, as a civilization, as one civilization on one planet, in order to flourish and to go out to the stars. So he would argue that, I think he did argue that maybe these other civilizations would have solved this problem. And so they would not expect a violent sort of interstellar, a violent civilization to come in, as you see in science fiction films, and try to take over everything, because violent civilizations like that don't really solve the problems that are necessary to build interstellar spacecraft. That's what. Now, whether he's right, you know, it's coming. Maybe he's being optimistic. The power of the Fermi paradox, ultimately, it's not dogmatic. It's the opposite of being dogmatic. It's saying, given that we have not yet observed anyone, what might the reasons be? And that's an interesting exercise. But it's not to say there isn't anybody out there. It's to say there's an observation here that we don't see anyone at the moment. So why might that be? So you're right, it might be everyone hides, or it might be that given what we know about the history of life on Earth, it's just very rare that complex living things emerge. Professor Brian Cox, Horizons, a 21st century
É
space
bué
odyssey,
possível essa cena
live
de
on stage.
simplesmente. Oi? Isto é só mesmo. Essa cena de simplesmente as civilizações destroem-se antes
One evening in the
de.
spring
Antes de conseguirem chegar à cena. Dilatação de tempo, teoria da relatividade de Einstein explicado. Pá, vou ver no mesmo vídeo. Isto é só 8 minutos, não vale a pena fazer um vídeo diferente só para isto.
of
Junto os dois.
1905, Albert Einstein, one evening in the
Isto é Science ABC, dilatação do tempo, teoria da relatividade de Einstein explicada.
spring of
Bota.
1905, Albert
Saí daqui
Einstein,
todos
then a
cultos.
mere patent clerk in Bern, after trudging through his day's work, decided to board a tramcar on his way
Guinness,
home.
e mete aí o vídeo que querias. Bem, este está mesmo com
Einstein would often wrap
animações
up his work
que
as soon
alguém
as
desenhou.
possible to contemplate the truths of the universe in his free time. It was one of these thought experiments
Senão
he
também
devised
vejo
on
este
that
e
tramcar
fechou as
that
reacts. Fazer
revolutionized
ou dois
modern
jogos de
physics
TFT e vou-me
forever.
deitar.
While receding away from the Zeitglogge clock tower, Einstein imagined what would happen if the tramcar were receding at the speed of light. He realized that if he were to travel at 186,000 miles per second, the clock's hands would appear to completely freeze. At the same time, Einstein knew that, back at the clock tower, the hands would tick along at their normal pace. For Einstein, time had slowed down. This thought blew his mind. Einstein concluded that the faster you move through space, the slower you move through time. How is this possible? Einstein's work was heavily influenced by two of the most iconic physicists of all time.
Não sei se
First,
concordo
there were
muito
the laws
nessa
of
cena.
motion, discovered by his idol, Isaac Newton, and second were the laws of electromagnetism, laid down by James Clerk Maxwell. Newton's laws insisted that velocities are never absolute, but always relative, so that their magnitudes must be appended by the phrase, with respect to. For instance, a train travels at 40 kilometers per hour with respect
Posso não
to someone
concordar.
at rest.
Olha que caralho.
However, it only travels 20 kilometers per hour with respect to a train traveling 20 kilometers per hour in the same direction. Or it travels 60 kilometers per hour with respect to another train traveling in the opposite direction at 20 kilometers per hour. This is also true for the velocities of Earth, the Sun, and the entire Milky Way galaxy. On the other hand, Maxwell found that the speed of an electromagnetic wave, such as light, is fixed at an exorbitant 299,792,458 meters per second, regardless of who observes it. However, Maxwell's notion seems incompatible with Newton's notion of relative velocities. If Newton's laws are truly universal, why should the speed of light be an exception? This presented Einstein with a daunting dilemma. This conflict between the ideas of Newton and Maxwell can be demonstrated with another of Einstein's brilliant thought experiments. Einstein imagined himself on a train platform witnessing 2 lightning bolts strike on either side of him. Now, because Einstein stands precisely in the middle of the 2 strikes, he receives the resulting beams of light from both sides at the same time. However, things get more complicated when someone on a passing train views this event while whizzing past Einstein at the speed of light. If the speed of light conforms to the rules of relativity, then the person on the train wouldn't witness the lightning strike simultaneously. Logically, the light closer to the man on the train would reach him first. A measurement of the speed of light made by both men would differ in magnitude. This would contradict an apparently fundamental truth of the universe. Einstein had to make a difficult choice. Either Newton's laws were incomplete, or the speed of light was not a universal constant. Einstein realized that the 2 notions could coexist with a small tweak in Newton's laws. To get rid of the discrepancy in the measurements, Einstein suggested that time itself for the
Estas
man on the
animações
train must slow
estão-me a
down
matar.
to
Este
compensate for the
Einstein.
decrease in speed, such that the magnitude remains a constant. Einstein called this absurdity time dilation, and his newfound theory special relativity. Newton believed that time moved unflinchingly in a single direction, forward. Einstein, however, had just realized that time stretches and contracts, varying with velocity. Due to its malleability, time, like space, deserved its own dimension. In fact, Einstein claimed that the 2 were one and the same. Together, they formed a 4-dimensional fabric or continuum called space-time, upon which the mundane events of the universe would unfold. Einstein suggested that massive objects like the sun didn't pull bodies like Earth with a mysterious, inexplicable tug, but rather curved the fabric of space-time around them, forcing Earth to fall down into this steep valley. A highly simplified analogy is the dip in a trampoline made by the of a bowling ball. If a marble were placed on that trampoline, the marble would immediately roll towards the bowling ball in the center. This is also true for Earth's gravity. We are pinned to the ground because space, so distorted by the Earth's mass, pushes us down from above. However, the slump in the fabric around Earth is not uniform, and Earth's gravity grows more intense as we move towards its center, where the curvature is at a maximum. Therefore, like the marble on the trampoline, an object that falls towards the Earth accelerates as it races towards the center of the planet. It falls faster when just above the surface than it does, say, when it is slightly above the atmosphere. But hey, according to special relativity, the faster you move through space, the slower you move through time. This means that time runs slower on Earth's surface than it does above the atmosphere. Now, because different planets have different masses, and thus different gravitational strengths, they also accelerate objects at different rates. As we have learned, this means a variable passage of time. This is what happens in the movie Interstellar, when the protagonists land on a planet in the proximity of a black hole. The gravity on the planet is so severe that...
Os buracos negros também são uma cena insane. As coisas que já vi, também passa-se lá bué da merda. Pô. E que de repente se entras num buraco negro, começas a ver não sei o quê da tua vida, dás um fast forward ou lá o que é. Eia bem, que tripalhada.
1 hour on the surface is equivalent to 7 years on Earth. To understand how motion affects time, let's consider the simplest timekeeping mechanism. A second passes each time the photon is reflected. Let's imagine 2 people, one in a spaceship slightly above Earth's atmosphere, and the second on top of a small hill just above the Earth's surface. Both are watching a man fall from space towards the ground. Let's say that the falling man is carrying the photon clock explained a moment ago. What do each of the 2 men observe as the man falls past them? What they observe is eerily similar to what a stationary person would observe when watching a ball bounce in a moving train. As the man falls from space, the light in his clock would appear to move in triangles to the two observers. This would mean that the light travels a longer distance, consequently stretching the duration of a second. It is obvious that the length of triangles the light traces, and therefore the duration of a second, is proportional to the velocity of the falling man. When we recall that objects closer to the center of the planet fall faster, we can determine that time would appear to pass slower to the man on the hill than it does to the man in the spaceship above. Of course, the difference is infinitesimal. The difference between the time measured by clocks at the tops of mountains and at the surface of Earth is a matter of nanoseconds. Time dilation affects every clock, whether it relies on basic electromagnetism or a complex combination of electromagnetism and Newton's laws of motion. In
Como é
fact,
que é,
even
Pantofox?
biological processes are slowed down. Yes, that's
Bem,
right.
fiquei
Your
completamente
head
perdido
is
com isto.
slightly older than your feet.
Isto já é bué de teorias para a minha cabeça. Gosto mais das teorias de conspiração de aliens e não sei o quê. Bem, maltinha do YouTube, já sabem como é. Não sei se foi o melhor vídeo. Fiquei uma beca perdida e há cenas que não sei se concordo. Mas pronto. Acho que conseguiria apresentar alguns argumentos, válidos ou não. Mas maltinha do YouTube, deixar aquele tal, deixar aquele lá em baixo, onde se comenta, e ver os outros e os próximos, tá bem? Vá, grande abraço e beijinhos. Mua, 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 mua.